Привет, Иса.
Привет, Тимур.
Ну, это почти Тимур.
М, Блядь, я не различаю голоса, господи. Она пока и сидите.
Good morning, everyone. Thanks for joining this lecture. So we are going to start in a minute or two. Let me join the session from the JavaScript so I could see your chat. All right, so it's time to start. And let me share my screen now. And hopefully, yep, we could start. So again, very welcome to everyone who joined our lecture. And today, I guess, we have the 5th lecture. Well, hopefully my enumeration is properly conducted. If no, please let me know. Well, today we are going to discuss what we started a week ago. I mean, the covariance and correlation topics. And plus, we are going to have some extra practice with the problem sets associated with these topics. And hopefully, if we are doing good, I will demonstrate you some basics problems that are usually presented at the wall exams. All right. So hopefully you are doing good, and all of the parts of the curriculum of this course are pretty transparent to you, and you have no problems with within your classes, and all the subjects are pretty clear. Speaking of the first module, let me highlight that the midterm exam is scheduled to be conducted on the Saturday, that is October 23rd. So it's gonna be Saturday, and we think that the exam starts at about 10 o'clock, and the total time duration is gonna be about 2 hours. The more exact details are gonna be published at the Telegram channel, but this is a pre-highlight for you, just to keep in mind that by the end of this month, we are going to have some midterm, a very nice one. All right, let's go back to business. And a week ago, we have said that 2 random variables may be distributed such that they have some dependence, or simply saying they have some association within each other. So basically, it means that the path of one of the random variables have some impact on another random variable. So basically, they have some association and one affect another. Under the assumption that we are studying and we are investigating the linear association only, we may apply 2 metrics to evaluate the strength of these association. And by saying linear association, I do mean that y could be presented as a times x plus b, where a and b are real numbers, and x and y in capital stands for 2 random variables. Brilliant. And both of these metrics were presented a week ago. So we said that covariance, that actually is a symmetric metric, is estimated as the expectation of the multiplication of 2 deviations of the first random variable from its own mean, as well the same with the other random variable. So basically, x minus the expectation of x times y minus the expectation of y under the expectation gives you a covariance metric. But this formula is pretty complicated, honestly. That's a pure definition. None of the researchers ever apply that definition. What they do apply is actually the bottom line that is slightly simplified and has more more presentable formula. So covariance is an expectation of the multiplication of two variables minus the multiplication of two expectations. And actually that gives you an estimator of the linear association. We have discussed that given that we are speaking now about the discrete random variables, so this is a discrete random variable case, then the expectation of something is actually transformed into a weighted sum, weighted within the probabilities. All right, so this is a definition of the expectation under the assumption that we are discussing the discrete random variables. And actually this stands for the covariance. If you'd like to play with that, and again, I did a very awful typo, here's why. Very sorry about that. So if you want to simplify this formula, you would get a sum of pi times xi times yi minus the sum pi xi times the sum pi yi. So actually, the same formula could be derived from the previous statement. And actually, what I had presented on this slide, what is just presented on that slide, is absolutely the same like this one. The only difference is that I had applied the definition of the expectation of the discrete random variable from these two lines, and I got that one. Going back to the properties of the covariance, I'd like to highlight the following. So covariance of x of itself will give you the expectation of x squared minus the squared value of the expectation. And actually that is a formula of the variance. And we know that covariance of random variable with itself is called to be variance by definition. So what does it say? You know that if variance is 0, then your random variable is non-random because it doesn't fluctuate at all. It is fixed. And once it is fixed, you don't need to guess any probability distribution because, come on, it stays the same model and you know the value it equals to. Although it must be positive by the definition, and if it is positive, then your random variable is random. And the more variance it has, the greater fluctuations are, and the greater deviations are generated by these random variables. If we are speaking about covariance, then we could distinguish 3 possible cases: minus infinity case, 0 value case, and the plus infinity. And minus infinity stands for the negative association. So basically, if you recall the linear association formula that I just presented, if covariance tends to the minus infinity, then we say that A tends to be a negative value. If covariance goes to plus infinity case, then A goes to +1, because these two variables are going to be purely covariated. And if your covariance tends to be 0, then A tends to 0 as well. And actually here, the main problem is the case, or sort of discussion, if we were given with 2 pairs of random variables, and someone says, look, the first covariance of the covariance of the first pair is sort of, say, 5, for example, and the covariance of the other pair is 15, so it's 3 times greater. Does this mean that the second pair has a greater association strength compared to the first pair? Well, if I were supposed to answer that question, I would say that probably no, or it depends, because covariance values cannot be compared because they do depend on the variance of each of the variance of each of the random variables. And the only way to apply the covariance metric is to say whether it is positive, negative, or 0. And that's it. So like we demonstrated on the previous property that on this slide, that under some assumption, covariance could be transformed into variance. Sorry, guys. Sorry. My bad. And well, it equals to variance. And the greater fluctuations are stored inside the random variable. The higher value of the greater value of covariance we are going to observe. And actually, this is the reason why we cannot compare covariance's values by itself. Instead, what was proposed next in order to overcome this problem was a correlation. But the correlation is actually sort of transformation trick in order to avoid all of these drawbacks, and we are going to discuss it soon. But before, let's highlight all of the properties that covariance possesses. Well, the first is symmetry. It is a symmetric metric. So if you evaluate covariance of X with Y and Y with X, well, obviously this is the same. And doesn't matter what association you're looking for. I mean, it could be either AX plus B or X equals alpha and Y plus beta. As you know, it's absolutely the same. The operations with constants. If both of your variables are multiplied by constants, then these multiplicators are going outside of the covariance and they multiply it by itself. And actually, this does underpin the statement that a variance of AX equals to A squared times the variance of X. If you recall the property of variance. Why so? Well, we know that covariance of AX with itself is actually a variance. And then you could do that transformation, then this, and then you get A squared times covariance of X with itself. And actually, covariance and variance, these are, well, it appears to be the same metric. I mean, look, even they are calculated slightly different. The sense and the intuition that is behind these formulas is completely the same. I mean, that covariance evaluates the co-deviations or co-fluctuations, I mean, common fluctuations of two random variables together, while variance do the same applied to one random variable only. But generally, they are well, generally speaking, I may say that covariance is a generalization of a variance. Sorry. And because it evaluates the co-movements and co-variations, co-deviations, if one of the random variables is a constant then a covariance value is 0. And well, this is obviously because if you apply the definition of that, it's here and of there. Well, then an expectation of constant is itself a minus a gives you 0, and then you got that you evaluate the expectation of 0 as a result. And then, well, as we said, a variance of x by definition is a covariance of x with itself. And now slightly more funny stories. A variance of the sum is the following. So I would say that probably the most useful formulas out of that list are these two. You are going to apply them a lot on year 2 of your studies. And actually this formula is going to be applied a lot once you start the course that's called econometrics. These are going to be very popular formula there. But currently, if we see that we want to evaluate the variance of the sum, I mean x plus y, it is a variance of x plus a variance of y plus a double covariance of x and y. What is funny, sorry. What is funny to recall here is actually that the intuition of this formula is very, very close to what you used to do when you were at school. Look, here I'm trying to mention some of the mathematical intuition and some of the mathematical tricks. A variance is a sort of a sum of squares. A variance, it is a sum of squares, and the covariance is a sum of multiplications by itself, generally speaking, very, very generally speaking. This formula intuitively looks exactly like a formula of squaring the sum. It gives you alpha squares plus beta squares plus 2 alpha beta. And what is funny is that the properties of these formulas are very, very close each other, and actually similar. In case if you have a minus here, the only minus that appears is behind the covariance only. Why so? Well, because if you were writing that formula, very general, you would have a variance of x plus a variance of minus y plus 2 covariance x and minus y. And then we're saying that if you have a constant, it moves outside of the variance being squared. And this, I mean, minus goes outside of the covariance without any trouble. So these are two highly important properties. All right. All right, let's try to do these very basic problem if we are able to solve it. So we have a box where we have 5 white balls and 8 black balls. All right, so we have 5 white balls and 8 black balls. 3 balls are randomly taken outside of it. Let x say that let's say that x is a number of white balls and the y is a number of black balls. All right, good. So we pick 3 balls on random. All right. And x is a number of white balls. So I could have 0 white balls, 1 white ball, 2 white ball, and 3 white ball. Well, if I have 0 white balls, then Y obviously is 3, here is 2, here is 1, here is 0. So without any problems, we may say that Y is 3 minus X, obviously. And if someone asked me to evaluate the covariance of X and Y, then I'm gonna say the following. Look, I know the definition of Y value, and I'm going to substitute it by the formula we just presented. Well, and this formula was actually taken from the problem set. Then I have a covariance that could be split according to the properties that we just discussed. And I have X and 3 covariated plus X and minus X. The first covariance is 0 by definition because one of the elements of the covariance formula is a constant. Then minus goes outside of, and I have a minus variance of X. Fantastic. Now, in order to evaluate these values, what I need to do, I need to estimate a variance of X. In order to do that, I need a marginal distribution. I need to have a marginal distribution of X. So let's structure the probabilities. The total number of balls is 13. What is the probability that I pick 3 balls and none of them is is white? So that's gonna be, the first ball should be black, then the second one should be black as well, and the third should be black as well. All right, good. What is the probability that all 3 balls captured are are white? So the first is white, the second, sorry. Then I have only 4 balls left in the box, so the second should be black as well. Once I had taken 2 balls, there are only 3 white balls in the box, so the probability to grab the third ball being white is 3 over 11. And since these probabilities are dependent, I do multiply one by number. All right, that's good. Now let's evaluate the probability to find just one white ball. So the first ball taken is white. Then I grab one black ball, and the third is black as well. And that should be multiplied by 3 because I may grab the white ball first, or the first is black and the second is white, or the first 2 are black balls and the white one is the last one. And because I have 3 possible combinations of the white and black balls, I must multiply by 3. And actually, very similar calculations are gonna be done within 2 white balls. So let's say that the first ball is white, the second ball is white as well, and the last is the black. But this, exactly the same story where this unique black ball is allocated. So it could be the first, the second, or the third only. And that's why I should multiply these by 3. And actually this gives me a probability distribution of X. So now let's estimate the expectation of X. It's gonna be 0 plus 1 times 3, 5, 8, 7, plus 2 times 3 times 5, 4, 8, plus 3 times 5, 4, 3. All right. If I simplify that, I'll have a common denominator, and we have 1587 plus 15 times 8 times 8 plus 15 times 12. Is it? Well, yeah, hopefully it is. And yep, so no mistakes. All right, then 15 goes outside of that, and inside we have 5 times 6 gives you 56, 8 times 7 gives you 56, here is 64, here is 12. 13, 12, 11. All right, let me then simplify this. I'm going to divide by 3. And inside we have 110, 120. It's 5 times 1, 32. 13 times 4 times 11. Then I will divide by 11 and by 4 again. And I have 15 over 13. So this is the expectation of x. All right. Then I'm going to recall a formula. The expectation of x squared minus the squared value of the expectation. And the last term of that was actually found. It is 15 over 13. And now what I need to do in order to estimate all of that, I need to have a value, I need to have the expectation of x squared. In order to do that, thanks, I have an iPad, I'm going to copy this. If I were writing that on the Blackboard, I have no idea how I would save the time, but hopefully I will do the following. Look, I am going to cheat, and here is a very nice trick that I'm happy to show you. I'm going to evaluate the distribution of x squared. If I square these values, the probabilities actually stay the same. And then I have 1 squared here, 2 squared here, and 3 squared here. So this slightly modifies the elements, and let's see what it gives me then. I will move it slightly to the right in order to combine it here. And well, then we have a common denominator, 13, 12, 11, 15 times 8 times 7, plus 4 times 15 times 4 times 8, plus 15 times 12 times 3. So if I did no mistake, hopefully, this should be correct. Then I will do the following. I will grab 15 times 4 outside of the brackets. So I'm going to grab 15 times 4 outside of the brackets. And inside I have 2 times 7 plus 4 times 8 plus 9. And here I have this get me 5, and that gets rid of. And then I have 5 times 14 plus 32 plus 9. This is 46 plus 9. It's 55, I guess. Oh, wow. So the 11 could be divided then. And we have 25 divided by 30. And here I write 25 divided by 30. And then once you calculate it, you have a final value. And here we just estimated a covariance of x and y. And because the increase of white balls pushes the number of black balls to decrease, the covariance is obviously negative, and you know that variance is always positive, but since it's multiplied by minus, it is obviously negative. And we used to say that covariance measure is actually a very nice one to capture whether the association is positive or negative, or there is no association. It is good. It is good. But some problems of that, I actually correlated with with the troubles to compare covariances between themselves. Actually, this is not the right way to analyze how strong is the association of two random variables and so on. So basically, to overcome this problem, what we do is actually we apply the correlation measure, and the correlation measure does not have these drawbacks. So first of all, it equals to the covariance divided by standard deviations of x and y. Hopefully you recall that sigma x is called to be standard deviation. And actually this gives you the more appropriate metric to compare whether your variables are associated or not. So now we know that the maximum of correlation is either +1 or -1. If it is a +1, then you have a positive association. If it is -1, then you obviously have a negative association. And well, basically this is interpreted in that way. If it is 0, then still you could say that there is no association of two random variables that you are analyzing. And now, because of these boundaries, it's much easier to compare them between themselves. So I mean the following. Look, if you have a pair of two values, if you have a pair of two random variables, you may say that if the association is close to 1, if the correlation is close to 1, then they obviously have a more observed linear association. If it is not that close to 1, you then say that statistically, the association is not that strong. So now we could say that a correlation of x and y equal to 0.9 is obviously better than a correlation of x and y equal to 0.7. Because it's closer to 1, obviously it is more strong. And this means that the association of these two variables is more obvious, is more transparent, is more evident. And the story is absolutely the same. Given that the correlation is close to +1, you have then a linear dependence. If it's close to -1, then it has a negative dependence. And if it is close to 0, then you have no idea whether they have any dependence or not. And now, I would propose to do some extra problems to practice these nice topic, and the previous one as well, before we go to the new part of the subject. So here we have 5 statements, and the question of mine to you is to text at the Zoom chat which of these 5 statements are true. Which of them are true and which are not? So it's a very basic question. If you don't mind, please do that within half a minute. So let me give you 30 seconds to have a look on this and claim which of these statements are correct or not. Yeah, this actually depends. All right, thank you very much. This actually depends on the definition of the probability. And here you have 2 random events. You have no idea whether these events are correlated or not. And what we need to check whether it is possible to have these probabilities or it is impossible to have these probabilities. And the first statement says about the union. So let me recall the formula of the intersection of 2 random events. It is a PA plus PB minus the probability of their union. And here it gives here it gives 0.7 plus 0.8 minus 0.9. So it's 1.5 minus 0. So it's, well, yep, it is possible. The first seems to be fine. No big problem about that. Then let's do the same. Let's apply the same formula to the second statement. So it gives you 0.3 plus 0.4 minus 0.8. And the result is negative. But you know that the probability cannot be negative. And then you say that it is impossible to have these probability allocation. Then I look to evaluate the probability of union. That is a marginal probability of A plus a marginal probability of B minus a probability of their intersection. And we have 0.8 plus 0.5 minus 0.4. So it's 0.9. Yeah, that's possible. How's about the last one? Well, the last one, oh no, the fourth one, sorry. The fourth one says 0.7 plus 0.8 minus 0.2. So it's 1.3. Yeah, it is impossible. And the fifth. And the fifth says 0.6 plus 0.2 minus the intersection, it's 0.5. So yeah, the fifth is possible as well. So the first, the third, and the fifth are all 3 possible. All right. So what I did, we just applied here a very basic formula that we discussed before. It's actually related to the probability of union. That stands for a very generic case when you have no idea whether the association are correlated, whether these events are associated or not, correlated or not. But we may apply this formula in order to analyze what values of probabilities we would expect to observe. And this claims whether it is from 0 up to 1 or it violates the definition. All right, here's a problem. So we have the office workers, and one of them, the first office worker, operates 70% of all letters and make mistake with the probability 8. The second one operates the rest 30% of letters and make mistake with probability 4%. Could you please evaluate a probability that the randomly picked letter has no mistake? Well, actually, this is related to the full probability formula. And let me give you half a minute for you to evaluate this value. And then I'm going to ask you to text that at the Zoom chat. All right, so let's recall the definition of full probability formula and evaluate it here. Well, we used to discuss that the probability tree is actually a very nice way to visualize the problem. So a randomly picked letter could be processed by the first worker or by the second worker. And the first worker is doing any mistake or no mistakes. And actually the second one is doing mistake or no mistakes as well. The probability of the first worker is 70%, of the second is 30%. The probability of mistake is 0.08, 0.92. The second one is 0.04, and here is 0.96. And we are looking for a probability of no mistake. So this comes from no mistake, and it was done by the first worker, plus no mistake, and it was done by the second worker. Here we have no mistake, given it was processed by the first worker times the probability of the first worker, plus probability of no mistake, given that it was processed by the second worker, times the probability of the second worker. Thank you, guys. So let's check that. The probability of no mistake is 0.92 times 0.7 plus 0.96 times 0.3. Yeah, superb. And this counts to 0.932. All right, so this is a total probability that randomly picked letter has no mistake. Now let me apply a Bayesian formula, Bayes formula, to ask you the following. Could you please evaluate the probability that a letter was processed by the second worker, given that a randomly picked letter had no mistake in it? So what has happened, we grabbed a letter on random and see that it has no mistake. And given that information, could you please estimate the probability that it was processed by the second worker? So hopefully you recall that this conditional probability gives you a formula of the intersection of two events divided by the probability of the condition. And the probability of being processed by the second worker given there is no mistakes is actually similar, or it's symmetric actually. And the probability of the condition we had already estimated, 0.932. So what is on the top of these fraction is actually that component. So here I'm writing 0.96 times 0.93. And actually it's 96 times 3 divided by 932. Well, if you simplify that and you calculate it more precise, you will get them a decimal value of this probability. But here it is, how it could be solved. All right. Now let's do this one. It was one of the very basic problems. So by the way, yep. Speaking of a midterm exam, you're going to have a multiple choice section and a free response section. And the multiple choice section contains about 10 very, very basic and simple problems. And this one was one of the multiple choice section problems, a very obvious one. So here you have a joint distribution. Here's your joint distribution.
So what does joint distribution mean?
A joint distribution is actually, so basically here is written a probability of u equal to, given that v is 0. So by saying joint, I mean the probability of the intersection of two random variables. So this is joint. When I'm saying marginal, I am saying that it is a probability of one random variable. And when I say conditional, I say that A is, say, conditional to B. So this is a conditional. We used to discuss these 2 lectures ago. So if you want to recall that, you should, if this is the 5th, then you need the slides of the lecture number 3. And what joint probability says is that it presents a probability of 2 events happening simultaneously. So for example, if I look on this table, I say a joint probability that u equals 4 and v equals 10 equals to what? So u is 4, v is 10.
1/10.
Their joint probability, absolutely, it's 1/10. That's right. And here we are presented with their joint distribution. Now let's do the problem. And we are set to evaluate the covariance. Well, covariance of u and v could be estimated as an expectation of u times v minus an expectation of u times an expectation of v. All right, good. The expectation of u times v is calculated as a sum across all possible outcomes, ui times vi. And actually here, what I'm going to do, in order to do that, I'm going to pass through all of these possible combinations. Look, with the probability 0, u is 2 and v is 0. With the probability 1/10, u is 2, v is 5. With the probability 1/2, u is 2, v is 10. With the probability 1/10, u is 2, v is 0. 2/5 is allocated to 4 times 5. 1/10 allocates to 4 times 10. Plus 1/10 allocates to 5 and 0. 1/10 to 5 and 5. And 0 to 5 and 10. Actually, if you were slightly more keen to that moment, you could say that the same formula could be written in another way. Why so? Here I used to enumerate these cells in a line in order to pass it. So it's this sort of the first, this is the second, this is the third, fourth, fifth, sixth, and here I have the line. We are going to solve this problem, and once we solve this problem, I will show you the second way how these could be computed. So actually, we are doing all stuff correctly. Now let's finalize the computations. Let's go to 0, 0, 0, 0. All right. Here I have 1 plus 10 plus 8 plus 4 plus what? Plus 5/2. Is it? Well, hopefully I made no mistake. If I did, please help me to find them. 11, 19, 23, 23 plus 2.5, so it's 25.5. All right, hopefully we had estimated a joint expectation. So this is called a joint expectation. Now let's calculate the marginal expectations. In order to calculate the marginal expectations, as you may guess, we need to know the marginal distributions. And the marginal distribution of U could be calculated in a very easy way. So look, I need to know the probability when U is 2, when U is equal to 2. U is equal to 2 at these 3 cases. So what I do, I sum it up and I get 6/10. Here I have 4/10, so it's 6/10 as well. And here I have 2/10. Did I all of that correctly? Or I made some mistake? It is 4. It's 4/10. So it's 6/10.
Probably the rightmost corner should be 1/10, and then it will be fine.
Look, unfortunately, we have not checked whether these joint distribution satisfies the prerequisites of the distribution. Look, I said at the very beginning, that this is a distribution of these two values, of these two random variables. If it was a distribution, then the total sum across all the possible outcomes should be equal to what? Well, it should be equal to 1. Now let's check the total sum of these probabilities. So 0 plus 1/10. Now let's recall a formula. Now let's recall the prerequisites of the probability distribution. The total sum of across all of the possible elementary outcomes must be equal to 1. 1, 2, 3, 4, 5. 5/10 plus 1/2 plus 2.5. And here we get 1 plus 1 point plus 2.5, 2/5. It is not equal to 1. Then here I should say that this table cannot be called a probability distribution table because it violates the definition of the probability. We said many times that the total sum of the probabilities across all possible outcomes must be 1. And actually, it was my typo. I'm very sorry about that typo. If you don't mind, let me slightly modify this. The only problem is actually related to that outcome. And here I'm saying that this is 0 as well. If I do that, then this marginal distribution is going to be 2/10. And let's simplify the calculations of the joint expectation. And then I have to simplify this one. So here is 0. And that 0 gave me these 8. So I should delete it. I divide 8 and I subtract 8 and I have 17.5. Again, very sorry about this typo. Now we cleared it. All right, fantastic. We did a check, and now we are about the necessity to check whether there is any typo at the joint distribution. All right, good. here's the marginal distribution. And let me calculate the marginal expectation of U. It's gonna be 2 times 6/10 plus 4 times 2/10 plus 5 times 2/10. It's 12 plus 8 plus 10. It seems to be 3. Am I right? Well, hopefully. I don't want to make too much typos, but if I did, please help me to allocate it. Now, let's do the marginal expectation of V. In order to calculate the marginal expectation of V, we need to know the marginal distribution of V. And here I'm going to write it. It's a 2/10, 2/10, and obviously it's going to be 6/10 here. The marginal distribution of V is 0 times 2/10, 5 times 2/10, and 10 times 6/10. It's 1, so it's 7. Yeah, it seems to be 7. Great. And now we may calculate the covariance. So it's 17.5 minus 3 times 7. So it's 17.5 minus 21, and it appears to be 2.5. So it's a minus 3.5, I guess. This is the value of covariance. What you could say now? Well, obviously you say, look, it is negative. And since it is negative, well, obviously they are negatively associated. And since they are negatively associated, you could say that the increase of U makes V to decrease. That's good. Well, now let's finalize this problem and evaluate the correlation of these two values. And in order to do the correlation analysis, we need to know the standard deviations of U and V. And I'm going to evaluate the variance of U and V first. And I'm going to cheat in the same way like I did in the previous problem. To evaluate the variance of U, I am going to estimate an expectation of U squared. And this is going to be done in the following way. So it's 2 squared times 6/10 plus plus 4 squared times 2/10 plus 5 squared times 2/10. All right, then I have 24 plus 32 plus 20 divided by 10. So it's a 56, 76, so it's 7.6, I guess. All right, let's do the similar with V squared. There's gonna be 0 plus 25 times 2/10 plus 100 times 6/10. All right, so it's 5 plus 60. So it's it is 65, is it? Wow, that's huge. All right. Now we see that we know a variance of U. Oh, no, I'm going to do it in purple. All right, so we are going to evaluate the variance of U, and it's going to be the expectation of U squared, 7.6, minus 3 squared. So it's 7.6. Well, it seems that I did a mistake. Oh, yeah, I did a mistake.
5 squared, 25.
Yeah, you are right. You are totally right. It should be 50 here instead of 20. And then it says that should it be 10.6? Yeah, seems to be. Yeah, it should be 10.6. Genius. And then we have 10.6 minus 9, so it's 1.6. This is the variance. Now let's evaluate the variance of V. It's going to be 65 minus 7 squared, 65 minus 49. It seems to be 16. Superb. Now we say that a sigma of V is 4. I mean the standard deviation. And the standard deviation of U is a square root out of 1.6, or it's 4 times square root of 0.1. Fantastic. And then we could say that a correlation of U and V, a correlation of U and V equals to covariance divided by 4 times 0.1 times 4. So that is our correlation value. Well, you finalize to calculate it, it's going to be obviously less than 1 in absolute values. It cannot be larger than 1 by the definition of. And then we got the correlation that could be analyzed in greater details. I'll say it that way. So here was a very basic and a very standard problem to identify the covariance and correlation. And here I just propose you to practice a very nice problem that was taken from the YOL exam. So the problem that is here is actually taken from the YOL exam. Let me give you half a minute to enjoy this problem, and then I'm gonna explain all stuff in very great details. All right, so try to do the first and the second part. The first part goes for the expectation of X, and the second part is, it has some more text, but still it's not a great problem. So let's evaluate the expectation of X. It's 1 times 0.5 plus 2 times 0.3 plus 3 times 0.1 plus 4 times 0.1. So it's 1 1.1 plus 0.7, so it's 1.8. In U policy in the hospital, we'll add exactly 1 day to the length of stay for the operation at every stay. Will the probable distribution of X change after this new policy put in the place? Well, actually, no, because what is said in these statements is that they are saying that it's going to be a new variable Y that shows the new duration of being at the hospital that is equal to the previous duration plus an extra day. So Y equals to X plus 1. And the linear transformation of the random variable has no impact on the probable distribution of it. And the new expectation of Y is going to be the expectation of X plus 1. That is the expectation of X plus 1. So it's 2.8 days. And that's it. Well, as you see, this problem was super duper basic and very, very obvious to you. So I hope you had no troubles to solve it. Now, speaking of YOL exam, that is going to be conducted in May 2022. So you are going to pass 2 YOL exams. 104A and 104B, two different exams. Each of these exams has two sections, section A and section B. And the section A has about 8 or 9 basic questions. And this one was captured from the section A, and that was enumerated like E, so it was the 6th problem. Very, very basic, not a big deal. And the section B, section B has 3 problems. They are usually called number 2, number 3, number 4. And you're supposed to solve 2 out of 3 problems from section B. So you have some option to choose what problems you want to solve. So what problems you want to solve out of the list given to you. So it's kind of an option. But instead of this option, you should be aware that there is no opportunity to renegotiate the marks given at the YOL exams, because the appellation does not exist there. But we will discuss this once we meet everybody on the offline office hours, hopefully. All right, so this was a very brief introduction to the example of YOL problems. This is another YOL problem as well. I'm going to share these slides at the Telegram group, at the Telegram channel, and you'll be able to capture these problems or to discuss. And now I would like to do a very quick introduction into a completely new area that we are going to elaborate in details at this month. And it's called the continuous distribution. So look, we've been studying the discrete variables, discrete random variables, and these are such variables that have a finite number of possible outcomes. So for example, like the previous problem with U and V, U had 3 possible values, V had 3 possible values, and they were discrete random variables. The opposite of that is, say that your variables has infinite amount of states, the infinite amount of states. And by saying infinite, I do mean that I may estimate I may evaluate your variables as precise as I wish to. And this presents us the concept of the continuous random variables. So now let's say that your random variable is possible, well, it is allocated at the continuous state space, and you may measure these variable as accurate as you wish to do that. An example of these variables are, for example, the temperature. Well, the temperature could be estimated as precise as you wanted to, as your equipment allows you to do that. And it's called to be continuous random variable. The time. A time could be measured in days, hours, minutes, seconds, milliseconds, and so on. And the time is also called to be continuous random variable. So by saying continuous, I do suppose to present a case where the accuracy of the evaluation of a random variable value is extremely high. And now the number of possible the amount of possible outcomes is infinitely large. Well, as a result, we start to discuss the distribution of continuous random variables. And in comparison to the discrete one, I should say that the distribution of discrete random variables was usually presented by the marginal probabilities, by the probabilities of precise outcomes. And now we are going to introduce the concept of cumulative distribution function. Well, a probability distribution function, a PDF, is applicable to play with a discrete random variable, while the CDF is more appropriate to model the continuous random variable. And what CDF means is actually the following. It is a probability that your random variable is less or equal to some threshold. Basically, under the assumption that you are applying this concept to the discrete random variable, it is basically sum across all possible states where your event is underpinned. So basically, if you say that you want to know the CDF of a discrete random variable, then it's basically a sum across all of the possible states that satisfy the event whether your random variable is less than some threshold. But what should we do if this amount of states is infinitely large? Look, you are moving from the discrete state space to the continuous state space. And what happens with a sum if you are applying it from, if you're applying that to the continuous random variable instead of the discrete one? It becomes to be an integral. And the CDF of the continuous variable, a CDF of the continuous random variable, is an integral of PDF from -infinity up to the threshold value. So actually the integral, intuitively speaking, it's, integral is a kind of continuous analog of the sum. And the definition of the CDF applied to the continuous random variable is actually an integral from -infinity up to x of CDF. And CDF, you mean, of a PDF, of the PDF. And the PDF, the F small, written inside that integral. So this tends to be PDF, and this is a CDF. And the PDF may be interpreted as analog of the probability of the precise outcome. So you may think that the probability of being equal to a precise value is this PDF. And then by integrating it, you basically sum across all of the possible values and you get the CDF. I'm going to stop by that moment. And the next lecture is going to start from this part. And we are going to discuss next week an idea of a continuous distribution. And the continuous distribution concept is going to be the last topic included into the midterm exam. So basically the October 9th is gonna be allocated to discuss the CDF and the continuous random variables. And the October 16th is gonna be spent in order to do some extra practice and pre-midterm preparation. Well, let me say thank you guys for your attention. Thank you for your efforts and for your trying to. Let me wish to enjoy your Saturday and your weekend. And hopefully we see each other in a week.
Thank you.
Thank you, guys.
Thank you.
you.
Bye.